Welcome to our first webinar on why mini-grid technologies need to be differentiated. To begin with, this webinar is a joint collaboration between three organizations: Energypedia, a knowledge platform for collaborative knowledge exchange on renewable energy, energy efficiency, and energy access topics in the context of development cooperation. The second organization is Hydro Empowerment Network, which is a knowledge exchange and advocacy platform for micro/mini hydro practitioners in South and Southeast Asia. The core support for HPNet comes from Vision Initiative at the Wuppertal Institute. And the third organizer is the SCAT Foundation, which was established by SCAT Consulting in 2002 to foster the exchange of knowledge and experience. And the webinar series is also funded by SCAT Foundation. About me, my name is Ranisha Basnit. I'm working as community manager at Energypedia. I, along with my colleague Heidi Fiebel from SCAT Foundation, will moderate the webinar. To begin the webinar, on the right side of your screen, you see a toolbar, and there you have an option called Chat and Questions. Please use this option to type in and ask us your questions, and also please tell us where you are from. We would love to hear about you. Now I would pass on the microphone to my colleague who will explain more about the webinar series and introduce our first speaker. Thank you.
Hello everybody, my name is Heidi Fiebel. I'm working for SCAT Consulting, as Ranisha already explained to you. I would like to give you a brief overview on the different topics which we selected for the coming webinars. So today we are talking about why mini-grid technologies, meaning PV, biomass, diesel, micro, mini hydro, wind and hybrid systems need to be differentiated. We will have a second webinar on grid interconnection of micro and mini hydro mini grids. So the question is, what is going to happen when the national grid arrives? This webinar is going to take place on 1st of June, and a third one is on productive end use, 3 examples of how to make it happen. This one is going to happen early July. We did not fix the date yet, but this is just to give you an overview. So our topic today, the first one, let me repeat, somehow everyone talks about mini grids, so do we today. But we try to differentiate and to better understand how and why to differentiate between the various options for electricity generation in mini grids. When selecting the topics for this webinar series, we found that micro and mini hydro is often overlooked when talking about mini grids. So we thought it's time for a fair and impartial assessment and a comparison of different renewable energy technologies for electricity generation in mini grids. We want to base on facts and figures and experience from different countries. We want to provide you an overview and a framework for comparison, including pros and cons, ranges of specific cost per kilowatt, of generation cost per kilowatt hour, what are the cost drivers and other parameters. So we would like to create awareness on these aspects and thus encourage those who design rural electrification programs and projects to be more open for all renewable energy technologies. So today we are going to have a first presentation focusing on micro and mini hydro, which will take about 20 minutes. Then you will have time for about 10 minutes to raise any questions or to give comments. As Ranisha explained to you, you should do that by writing on the chat box. Then we will have a second presentation, which is focusing more on PV, diesel, hybrids, biomass, and wind. Again, 20 minutes presentation. And then, personally, I'm going to give you a short overview on the so-called technology comparison table. And then you will have the possibility to ask further questions on the presentation and on this summary table. So at the end, we will conclude with a few key aspects that have been discussed and with the closing remarks. I just get the message that our first presenter is not yet online. Since he's far away in the United States, maybe he had some trouble to come early to his office. So I would now say we start with the second presentation, focusing on PV, diesel, hybrid, biomass, and wind. This presentation is going to be held by Xavier Valvé. He is the co-founder and director of the engineering and consultancy firm Trama Tecnoambiental in Barcelona. He has more than 25 years of experience in renewable energy, rural electrification, and distributed generation projects, autonomous as well as grid-tied, renewable energy hybrid technology for islands and isolated villages. So he has a broad background to tell us a lot about renewable energy technologies in mini-grids. So I will give the floor to Xavier, and thank you very much for joining. So may I ask Ranisha to switch the screen to Xavier?
Hello, good morning, everyone, or good afternoon for some of you. I just would like to welcome everyone into this session. Just a second. I think, can you? Yes, I don't see my screen properly, but
Hello, Xavier.
Yes.
We can see your Skype screen, so if you could put up your presentation, we'll be able to see your presentation.
Okay.
We can right now see your Skype.
Yes. Okay.
Yes, now we can see your presentation.
Okay, thank you so much. So I wanted to share a presentation on mainly solar mini grids, and we are a small company in Barcelona, but that have been involved in rural electrification for many years, of grid electrification, and in fact we started back in the late 80s electrifying rural farms and households in southern Europe, basically in the Mediterranean area, southern France, northern Spain. But then after doing some solar microgrids in the Pyrenees and in Andalusia, we started to develop solar mini grids in different developing countries. Although initially we are our vocation is to be consultants and engineering specialists, in many projects, especially working with multilateral agencies or NGOs, we have ended up delivering the final infrastructure in many cases. Okay, so we have been exposed to not only the framework of the projects, but the practical experience. And I wanted to share then some of this from the last few years of work. So an aspect would be trying to define a solar mini-grid, which, it's the same that for a lot of mini-grids, but in this particular case, maybe I want to introduce another concept that I'll repeat later, which is that not necessarily what I define as a solar mini-grid or a solar hybrid mini-grid is all the households or clients that are interconnected by a wire. I will come back to this later. In this case, the generation is based on solar PV, which is an intermittent source, of course. That means that either it is hybridized with a genset or it has batteries to be able to provide a steady level of electricity service. And sometimes we see that the needs grow or change, so it's interesting to design and take into account the expandability or the clustering or interconnection between mini grids or the mini grids and the grid. Regarding capacities, we would be talking about between very small ones of about 5 kilowatts to the range of hundreds. The distribution grid is in general low voltage. This maybe would be a difference between solar and mini hydro, for example, because often with solar we can embed the generation in the village, even as distributed generation, as opposed to technological options where maybe the generation is not exactly in the middle of the village. It's at a certain distance and you need to have medium voltage lines. The distribution can be single phase or three-phase grids, although now there are starting to be some experiences distributing DC instead of AC. And a mini grid usually is under a certain business scheme, which can be of different types. And there have been innovations in the billing and payment methods, because we have a challenge here, which is that we not only have limited power, limited, say, amperes or watts of capacity, but we also have limited energy because the energy that can be generated is directly related to the installed capacity of PV modules and the amount of sun. Therefore, we need to manage this sharing of a limited resource without conflicts. That means that this has to be well discussed, and there is the need to do some social work at the village level. I wanted also to share some thoughts regarding the attributes of PV technology, because I think that understanding what the attributes of a technology or a source are can help you to see where you are more competitive. The most important one for me is the universality of the resource. I will get back to that later. The other, it could be the simplicity and modularity of this technology, in the sense that it has no moving parts, it's all static, solid state. Although later we will see that there is a particular challenge related to batteries. Reliability, the social environmental benefit, this is common to all renewable energy technologies, and its cost effectiveness in some applications. So we have to try to identify which applications we are cost effective. I will not go in detail into all of those attributes, but I want to share the one that for me is the more particular to this technology, which is the universality of the resource, which means that you are not as site specific as other renewable energy generating technology, and this has implications. One of them, for example, is what I said earlier, that you could embed the generation within a village. You could put it in a power plant, or you could put it on the roof of some of the buildings, as opposed, for example, to biomass, where it is an option in places where you have access to abundant biomass, but you need to clearly identify the resource and it's site specific. So when trying to compare different generating technology, in the case of solar, maybe at the feasibility level, more or less it's straightforward. In the case of biomass and also wind, we need site-specific evaluation. And also there are other technological considerations where, for example, it's more labor-intensive. But in places where there is a lot of biomass, it can be also cost-effective to consider this generation technology. with small wind turbine mini-grids, you are again in a site-specific resource that needs to do proper siting and choosing of the tower height. You have to see if you have the resource near the place of consumption, because if sometimes it may be that the wind is available and on top of the hill, but the village is in the valley. And for large-scale wind generation, there is economies of scale. But for small wind generation, if you need to run a long distance between the wind turbine generators and the site, then you lose a lot of cost effectiveness. Another issue with wind is that the power of the machine is related to the cube of the wind speed. So a small difference in the assessment of the wind speed can make a big impact on the output of the generators. In our experiences, most cases that we have combined PV and wind, it has been because we have seen a certain seasonal complementarity, that some periods with more sun have less wind, and periods with less wind have more sun. But if this complementarity does not exist, often with lower prices of PV modules now than 5 years ago, it is difficult to have small wind compete against the generation with PV. From the point of view of environmental impact, this is also an interesting aspect which is common to all renewable energies, and PV, of course, is not as from the point of view of primary energy consumption per kilowatt hour produced, is not as good as wind or hydro, but still is very acceptable level. And of course, to assess these indicators is very specific of where the PV modules were manufactured and what was the primary energy source of the country where the modules were manufactured. The same with other indicators like CO2 emissions. But another environmental related aspect is that often energy generation projects require environmental assessment, and this is particularly necessary for the case of hydro, because you have to, or biomass, because you have to assess the impact that you have on the resource. In the case of solar, you don't have a direct impact on depleting the resource, so you could go into let's say, standardized environmental impact assessment recommendations, which would be more related to the end of life waste management than the construction phase. So instead of having to go through studies of environmental impact side by side, you could have general type approvals. Back to that vision that I shared before, that I mentioned before, on that a mini-grid may not necessarily be that all the clients are connected to the wires. It's a result of what I said earlier, that you have a universal resource. So if you are in a village, you have the sun shining on all the roofs of the village, or all the surface of the village. So at some point, you also have clients with different needs. You have clients which, with a relatively low level of service, you cover their needs. Let's say basic light and charging of a cell phone, or clients that need more power and more energy to do productive activities. So even the cost of interconnecting them with a low voltage distribution grid to this power station may not initially be necessarily cost effective. So you could, since the sun is shining on all the roofs of the village, you could, under the same business model, have some clients that you service them with individual installations that you as their needs grow, then you connect them to the main grid. This is a possibility that gives you modularity, and since the PV modules also are the same, so when you connect them, you take the modules, and instead of having them in the roof of the client, you put them in the power station. So this is a flexibility that I think is a difference between this technology and the other more centralized generation options. Other aspects are critical success factors for projects to be sustained over time, and this also is an issue that we could go on discussing different details, but I just wanted to highlight some aspects which may be more specifically relevant to solar PV mini-grids. This is that, for example, demand characterization is quite critical, because you size, because of the modularity, you really can size your investment and your capacity to match the needs of that demand assessment. For example, in the case of hydro, you may end up that your civil works, the marginal cost of, if you have enough resource, the marginal cost of oversizing your civil works is very little, so you may want to oversize it, and then if the demand characterization is a bit underestimated, is not a problem to enlarge the hydraulic part in the future. But with PV, you really have to. It has a bigger impact, because you choose your capacity according to the needs, and everything is modular in a PV solution. But what is less modular and it's less expandable, or is not as easy, is the battery. Okay. Then also in these success factors, of course, the business model, the regulatory framework would be common to all mini-grid technologies, procurement, logistics, operation and maintenance, the same, but maybe also the metering concept may be a bit different in the case of PV. I will get back to this later. Regarding procurement and logistics, the construction of a PV plant can be done very, very quickly. Usually the limiting factors are securing the financing, in some countries the permits, but the construction itself, it can be very, very, very quickly. To understand the demand, in our case, back since 2004, we started to use different categories of clients. This is an example. So what we called at that time category A would be the very basic household needs, which is usually the higher number of connections, and the most probable power per connection, it's around 100 watts, the consumption. Maybe it can have surges of 200 or 300, and we are looking at less than 1 kilowatt hour per day of consumption. So this gives you a load which is basically illumination, communications, and it's very rigid. It's a load profile that you cannot do too much demand side management.
Excuse me, Javier.
Yes.
Sorry, we are already over time. So is it possible for you to wrap up your presentation in the next 2 to 3 minutes? Sorry about that.
I will try. Thank you very much. Okay.
Thank you.
So these are some examples of categories, but the higher the level of service, the more flexibility you have to manage the loads. And this is another table where we compare here what we call the energy daily allowance and the maximum power for the different categorization. Now there has been initiatives by NREL and by also the Swedish Cooperation to define other tiers. So this is an equivalency table that I'm sure that there will be more coming in the next few years. Okay, here is a typical plan configuration. Another issue, it would be, for example, that we have batteries, and designers prefer to have extra low voltage for batteries. That means going up to 48 volts or that order of magnitude. If you go above that, you have to meet other electrical requirements regarding safety, which have to be accounted for, especially in a rural setting. Battery handling becomes one of the particular issues of this technology or any intermittent renewable energy technology that has to use batteries. And there are very typical different tariffs, but usually we recommend a flat rate subscription, similar in a sense to what you see in hydro mini-grids, but in this case with a limited amount of energy per day. I go through this one quickly. Another factor that affects cost is whether, when you have a hybrid PV plant, what we call the renewable energy fraction. So it could be that you just complement, you offset part of the fuel consumption, and the genset is almost always on, or it could be that the genset is off and only for backup. So this will impact the investment cost because you need more batteries. And regarding the cost structures, although when you hybridize, you may end up with a relatively similar cost per kilowatt hour, depending on your location and investment cost. The thing is that with gensets, you have a very high operating cost, which in the case of a PV generation with backup, most of the cost is payback of the assets. So depending on your capacity to pay, the thing is that just with tariffs, you can sustain the service. This is a key issue, which we don't see in genset alone. Cost structure for investment is generation, distribution, grid, storage capacity, and the conversion, like related to the demand. But logistics and maturity of the market play a big role. So even if we see decreases in PV module prices today, we don't see those being reflected in mini-grid development because a lot of the cost is still permits, lobbying, customs, etc. This is just a sample of some costs analysis. A case study of a recent project in Ghana. This is just to share some information with you that you can analyze later. And quickly, a few pictures to finish on a village that has been operating since 2012. This is in Africa. It's an island village in Cabo Verde called Monte Trigo. These are the different service levels offered. This is watt hours per day. This is the monthly fee. And this is the typical aggregated load profile, where you see that most of the load is in the evening, which means that all the generation of the day has to be stored into the battery. One interesting aspect is that, well, it's a relatively small install capacity, but it serves quite a few number of households. But because of the fact that it's a static generation, in this case, the PV generation is a pergola structure in the patio of the school. So really it provides shade to the schoolyard. And that was an added value, this shading, and also the modularity of the design, that it could be expanded 1 year later when 20 more clients signed in. Since sometimes you have surplus generation during the daytime, then in this case we make ice, and this ice is used for fishermen for fish conservation. Recommendation is to engage the users in the project, details on the technical room, distribution grid, and very important to train the users in using electricity, and also local upkeepers to keep the assets in the best shape as possible. And well, I tried to wrap up a lot of information in a few words, so I hope that the message came through. Thank you very much, and please let me see if you have any questions.
Okay, thank you very much, Xavier, for this very interesting presentation. In the meantime, we got a few questions regarding your presentation. I clustered them a little bit just as the first information. I would like to tell you that we are going to make these 2 presentations plus the overview table, which I'm going to present at the end. We are going to make that available for you, so you can get it through the internet, and you will also get an email where to download all this information. So don't worry, you will have access to that information later on, and also the whole webinar is recorded so that you can also listen to it again. So Xavier, the questions which came up, the first one was related to this challenge of sharing energy in the village. You said that this is often difficult. The question is there any technical solution which you could recommend? And there was a second question which was somehow related to that. Is there a general recommendation on flat rate or on prepaid systems? So this first question is somehow related to sharing of energy and the different tariff systems. The second question which came up was about the purchase of the components, in particular for the PV panels. Is that normally, the question was actually, is it purchased in Spain, or do you get that from China, or how is that, is there a competition between different equipment producers? And the third question is related to the hybrid systems, how you optimize the renewable energy part in hybrid systems. So how do you maximize the renewable energy part? You explained that a bit through the cost. You said the cost is similar if you use higher running costs for an additional diesel generator, or if you have higher investment for the PV part. Maybe you can elaborate a little bit more on how to design the hybrid system in an optimum way.
Okay. Okay, thank you. So regarding the metering and sharing of the energy, the issue here is to first of all, from the beginning, to work with a potential client, explaining that there will be a limited resource, and in general, since our first projects, this has not been a problem. And what we identified is that it was clear to use in many villages the analogy of water, because they are used of managing water, which is limited. So they have already rules regarding how many, say, liters of water per family they manage, or so on. So what we developed was an algorithm which limits the amount of energy per day. This concept we have called EDA, Energy Daily Allowance. And in reality, it does not give you the energy at once, and you're disconnected once you have used it up. It's like a drip charging of a smart meter, so you always see your balance of energy that you have available, and if you consume too fast, the level goes down. If you consume moderately, it stays at the level that you have contracted. And if you save, you see the level going up. So we manage the power, the amps, but also the energy. Regarding the prepayment or that, or the type of rates, I recommend, or we use flat rates, because most of the expenses are fixed. Are the local salaries paying back the investment, paying the overheads, and very little of the cost is related to variable costs like using fuel. So you want to try to have a predictable revenue. But the flat fees or subscriptions are related to the level of service that you have contracted. Now, regarding the components, in general, we use any components that that meet certain quality standards in the market. For us, what is important is that, of course, they meet the engineering criteria of the design, but we also look a lot about the companies behind them, that they are reputable companies, because we have seen in as opposed maybe to other technologies, in the PV there was a big, quick growth, which created a lot of new companies, and that disappeared after 2 or 3 years. So we give a lot of importance to companies that if you need some replacement or expansion in the future, they are still around to provide the service. Regarding the optimization, or what is the optimum, what more or less happened was that since the price of PV modules has gone down a lot, and on the overall cost of a mini-grid, as I mentioned, there are a lot of soft costs regarding maturity of the market, logistics, etc. It's gotten to a point that the PV module itself is relatively the share of the investment cost is relatively lower now than what it was 5 or 10 years ago. So that means that we tend to oversize the PV module, which means that the genset almost ends up being a backup, and that the batteries are always kept at a higher state of charge, which means they will last a longer time. When PV modules were relatively expensive, the optimum levelized cost of electricity was in the order of 70% PV generation, 30% genset. But today we are almost designing most of the projects for almost 100% PV generation, or let's say 95%. I don't know if there was any other question, Hedy.
Thank you, Xavier. I think you repeated all 3 questions. There are much more questions coming up. The problem is that we would like to, yeah, the time is very limited. I'm sorry for that. But I would suggest that we continue with the next presentation, because fortunately now Bikash is also among us. So I suppose he can also hear us. Bikash is going now, with him we are going to switch technology. Now we come to micro and mini hydropower. The title of his presentation is "Under which conditions do micro mini hydropowered mini grids remain attractive compared to other mini grid technologies like those which Xavier just introduced." So Bikash Pandey is Director of Innovations for the Clean Energy, Environment and Water Group at Winrock International. Bikash's work experience encompasses 20 years in policy review, design and implementation of a range of clean renewable energy projects in Africa, Latin America and Asia. So I'm very happy to say hello to Bikash Pandey. I would ask Ranisha now to switch to Bikash's screen so that you can follow his presentation.
Hello?
Hello, Prakash. Could you also share your screen with us? We can only hear you.
Okay. Do you want me to have the presentation on my screen?
Yes, please.
Okay. Just give me 1 second. And could you remind me again to, okay, show my screen.
Yes.
Yep. That good?
We
Can you
have
see it
not
now?
been able to. No, we still don't see. Okay, now we see your screen. Yes.
Okay. And
Thank you.
there should be a way to put this on show mode, or is this good enough?
I think it's good enough. We can continue with this. Thank you.
All right. So good morning from Washington, D.C., where I am. Apologies for the delay. Let me go quickly through the slides. So essentially, I'm looking at the specificities of hydro as a mini-grid solution and where it remains quite attractive. This is in the context of hydro, microhydro, mini hydro, still I think being the dominant mini-grid renewable energy technologies in terms of numbers, but with technologies, particularly solar, coming up as perhaps faster growing. So the question comes, when is hydro still interesting, and when should you think about some of the other technologies? So I will try to focus on that. Here's an example of a hydro project that has been serving the town of Namche Bazaar on the way to the Everest mountain. This is the 3 villages are supplied by this 630 kilowatt plant, about 800 homes, and supporting tourism and tremendously adding to the economy there. Significant improvements since the electricity, both in terms of water treatment, tourism hotels, handicrafts, certain tourism-related industries. So a good example of quite extensive use of productive end uses and has really been able to add value to tourism. This is in eastern Nepal and over 20 years old now, serving that community. So the main parameters are investment costs, critical as a upfront barrier, price of energy, very important in terms of how people can use the energy and how much. Productive use and load management. There's some specificities to hydro around how the loads can be managed and how productive end uses can be enhanced or increased. The challenges of operation and management of hydropower schemes, and then specifically some issues that are specific to hydro mini grids. So the investment cost of hydro perhaps is the widest of the other different technologies. It is oftentimes among the cheapest. It can also be among the most expensive in terms of investment costs. And the reason for the big range is that there are such a thing called good hydropower resources. As Xavier just pointed out, unlike solar, hydro and wind technologies are very site specific. So good hydropower site is quite different from a poor hydropower site. And I will come to what makes a good hydropower site in the next slide. So hydro can be very inexpensive, although at the low end, $500 a kilowatt to $1,000 a kilowatt, oftentimes the experience is that these plants are not producing the full kilowatt hours as advertised. And so in terms of the energy cost, they may not be that much cheaper, although in power installation they look cheap. And also hydro, the site specificity, one of the big factors is what is the cost of the civil works of hydro, and that can vary quite a bit. Also, hydro kind of requires there to be a sector in country with experts in country. That is where it does the best. And if you have to import that expertise or buy the turbines or the pipes all from outside, that tends to push it also to the high expense rate. Whereas you expect for solar to import the bulk of the components, for hydro it makes a big difference if you can produce most of it in country. And one issue about sort of scaling up, because the civil works particularly have some economy of scale. If there is enough water in the river and you expect that the load will increase, Xavier already mentioned this, that it may make sense to oversize the civil construction in the beginning, since it's still the same weir. The canal construction doesn't go up that much when you increase the size. And then later on, once the demand increases, you can add a turbine or generator, sometimes even a new penstock, an additional penstock pipe. So here's a typical schematic and the components, starting at the intake, where there is oftentimes a weir or a low dam. These are run-of-river hydro. Head race canal can be either an open channel or a low-pressure pipe. The 4-bay tank, sometimes there's a reservoir at that 4-bay tank. If there is space there, in order to be able to extend the water resources and put in a larger power plant, or compensate for the fact that in the dry season there may not be sufficient water. The penstock pipe, metal, sometimes plastic. This is the pressure pipe that carries the water to the turbine. And then there's of course the powerhouse and the tail race to take the exhaust water down back to the river again. And you know, transmission distribution, sometimes there's a transformer there if the distance to the load is far off, or if the power required is higher. So what makes good hydropower resources? For those who may not be as familiar with the technology, generally we are seeing microhydro, mini hydro, anywhere from 2 meters to 200 meters. Generally, the higher the better in terms of head, the drop. Just going back to the last slide, a couple of things I should point out. When we're talking about the head, we're talking about the elevation difference between the 4-bay tank and the turbine. So it is the difference in elevation between these that pushes the water, that provides the pressure. And so if you can show, if you can find a site with a large drop, you know, that provides a lot of power, power being a product of the flow rate and the head. So, and if you can produce that high head with a short canal, essentially the canal makes up the cost, and the head makes up the pressure. So, you know, for a lower cost, you could get more power. So the per unit cost again goes down if you can generate a high head for low length of canal, which basically translates to the slope of this river. So if the slope or the gradient of this river is high, which means it's a steep river, which means for a short head race you can have a lot of head. That generally makes a good site, just because you get more power for less water, and or you can produce a lot of power, so the per kilowatt price and the per kilowatt hour price both tend to be low. So that was the second point, river gradient or slope, higher the better. Civil works, big difference here. It is expensive generally to build protection from landslides and floods. If you have a nice intake area with shielded by a big rock, I mean, oftentimes the construction price comes down quite a bit. Geology is important, mainly if you're talking about the difficulty of building the canal. In very few instances, there's sometimes a tunnel in the head race. Again, geology extremely important for that to keep the cost low. And the head race, if you don't have the need to build aqueducts and other types of structures or protect from landslides, that reduces the cost. In terms of hydrology, when hydro is designed, once you have done your demand analysis, we are looking, these are isolated hydro, not connected to the grid. So we are oftentimes looking for design flow to be available at least 10 months a year. However, this is not always possible. So in certain instances, you may have a site that only has the design flow available for 6-7 months of the year. But if you have a space to construct a reservoir, then during the months when you don't have full flow 24 hours, you can store up the water to use for, either just for the peak hours or use it as per need, so that with a governor controlling how much water actually is let into the turbine, so that you can actually save on the water when it's not actually needed and save that up when it is actually needed during peak hours. So just to give you some idea of some different types of sites. So the picture on the left is a relatively high head site. It has a waterfall, so that makes for a nice gradient already. Waterfall is, very short distance and a big head all in the same place. In that particular example, there is really no headrest canal, just the penstock pipe right from the intake. Picture on the right is from Afghanistan, where an intake is put, front intake right in the river there. And, fairly big civil works here, knowing how the floods that come in this river. Picture on the bottom left, nicely built canal from Indonesia, made out of concrete. Many countries, for the small systems, these can just be also clay canals, mud canals. And some of the costs of traversing difficult areas is on the final picture on the right. Local manufacturing brings down the cost quite a bit, but it does require investment. So one of the big things with hydro is that hydro flourishes in countries that have a strong local manufacturing base, local expertise. So very hard to do pilot hydro systems in countries, unlike solar. So because the cost difference is large, and the repair capability and the support capability is not strong if you are just doing 1 or 2 pilots in a country. Much better to have a sectoral approach. And again, there solar has an advantage in a certain sense, since so much of the equipment is brought in from the outside. It's very easy for the local sector to be built up to have the capability for installation and upkeep. So let me get to the key point here that I'm trying to make, is that the huge advantage of hydro, and whenever you have the resources, it is why it is the preferred technology, is that the price of energy can be quite low, down to 5 cents. Can also be higher, as I mentioned, with some of the higher cost plants. And why that energy cost is low? Well, most importantly, hydro can produce 3 to 4 times as much energy, kilowatt hours, per installed kilowatt compared to solar and wind. So, hydro can run 24 hours a day. Solar typically, effectively 6 hours a day, or wind maybe 8 hours a day. So hence, for the same kilowatt installed, you get a lot more energy. Of course, the challenge is, how do you use all that energy? Because any energy that is not used is wasted. And that 3 to 4 times as much energy doesn't really add much value if you cannot use that energy. So the trick and the fundamental thing here is how do you increase the plant load factor of a hydro plant? Because the higher the load factor, the cheaper the energy effectively becomes. And because the running costs are low, and you don't have fuel, you don't even have batteries to replace generally with most hydro schemes. So there's a kind of a circular effect here that the low cost of energy actually enables productive end uses. At the same time, the higher revenue from productive loads means lower cost of energy for everyone. So if you're putting in hydro and taking all the trouble to build up a sector, really important to think through how do you build in the productive end uses. And one key issue here, since the power is available 24 hours, so very important consideration for hydro is that it is not so much the kilowatt hours that is expensive as the kilowatts. So during peak hours, everybody wants the kilowatts, so that's in short supply. But the kilowatt hours during the nighttime and during the middle of the day are inexpensive. They're almost free. So hydro oftentimes tends to have pricing based on a fixed subscription rather than kilowatt hours, because the kilowatt hours is relatively inexpensive and the kilowatt hours is expensive. So sometimes the pricing is done just for the kilowatts. So a subscription of 100 watts or 200 watts or 300 watts puts the onus of high utilization on the user. So that's a simple way, plus you avoid the cost of a meter. I'll give you an example of the picture I showed early, the Kumbu Bijuli Company, well-established project. And so here's what they have done in order to increase the load factor. So this is high up in the mountains. Firewood is very expensive. So they wanted to figure out how to use that electricity for cooking. And so what they did essentially is they have got two tariff levels, levels 1 and 2, which have average, the subscription I will show in the next picture, 100 watts or 1260 watts. And these are available 24 hours for the same price. So there's no metering with them. And so it's up to the user what to do, and the project promotes water heating and cooking during the off-peak hours. Then levels 3, 4, and 5 and the industrial level, these are metered. And also, again, there is a demand charge, again, to discourage people from, signing up or putting in equipment with a high demand. So the focus always is to try and spread out the load, get people to use lower kilowatt demand, but use more kilowatt hours over time. The off-peak level 1, off-peak level 2, actually they use a lot of their off-peak energy for water heating. So, thermal energy relatively, you cannot charge people a lot for that, but if it's during the off-peak when the energy is more or less free, it makes a lot of sense to do it in that way. Next slide, just to show these tariffs are from a few years ago, so they may have increased, but essentially you can see the main idea here. So the two tariffs, number 1 and 2, are considered social tariff. 74% of the customers are within that. The 100 watts is for very poor households, and they only pay 60 cents US per month. So relatively cheap price, and there is no metering. Second tariff, just over a kilowatt, can power a kilowatt cooker or heater. And they have a flat rate of, again, $6 a month. There is a provision for the second group to be taken out during the peak hours. So their power availability actually goes down during the peak hours. And then the commercial, number 3, number 4, and number 5, they have a demand charge, which is a flat rate, US dollars of $3, $8, and $30. And then on top of that, they have also a kilowatt hour charge of about 7.5 cents per kilowatt hour. So there's a demand charge to try and keep the demand low, and then the energy charge for actual usage. So, so yeah, I cannot stress enough for hydro that, you know, how you manage the productive end uses, the load management really makes it very effective. At the same time, I must say, you cannot get these prices for solar, wind, etc., just because of the amortized cost of the batteries. Extremely important point here. So this cycle of low energy, which means more productive end uses, which in turn means low energy, is really the key of what I want to get across to you today, if it is one thing you carry away. On the operation maintenance, hydro is a relatively simple technology, so village operators can be trained. Systems can also be owned and managed by village committees. They're also seen as, by many programs, as a way to build social capital for communities to put a lot of inputs because it has a high local content. And oftentimes the higher subsidy programs, the non-commercial programs provided by donors and government require community ownership, keeping in mind equity that government doesn't oftentimes feel comfortable giving grants like this to entrepreneurs. They rather give it to communities. The specific challenges of hydro is it can take quite some time to construct. You need to have measurements of the resource, at least one dry season flow. There is really, it only makes sense if you're investing into the entire sector, as I mentioned earlier. And so the challenge, the last point I was making about the social capital is an excellent issue, that, you know, social capital is great, but it requires investment. And oftentimes, when it is not available, or sometimes even when it is available, community management tends not to be as commercially managed and pushing that productive cycle, low energy loop as strongly as privately managed systems. Although I have to say there are exceptions. KBC itself is a community managed system and does very well, but there was extensive input put into the capability of that community to get to this point. So thank you.
Okay, thank you very much, Bikash, for this very interesting presentation. I have a few questions from the participants. The first one is related to how you assess the flow if there's no flow data available at all. I mean, you mentioned there should be at least one dry season flow. This is really the minimum. At least one has to go to the river to make a flow measurement at the end of the dry season. But in general, can you give any recommendation on that?
Yes, so there are different ways. Sometimes what is done is that a larger river close by, you know, where there are flow measurements, oftentimes those are taken as a proxy, and you know, you can look at the ratio of the catchment area of the larger river compared to the smaller areas. So if there are other rivers that have long-term measurements, that is a good indicator to go by. In some countries where the rains are pretty reliable, people actually have, you know, rules of thumb about what the minimum dry season flow is, and almost a flow duration curve can be drawn just based on the catchment area once you know the general rainfall in that particular area. But, you know, generally you have to go to the site to look at the intake sites and all of those anyhow. So ideally you want to time that during the dry season and try and take a measurement, and also consult with the local villagers in terms of how that compares with previous years. So those are typical good practice.
Okay, thank you. The second question, I think it can be easily repeated. It's why you don't have just a long penstock instead of having a channel and a penstock. I think it's mainly the cost aspect, that it's normally cheaper to have a channel as civil works instead of having a long penstock. Is that correct? Yeah.
That is correct, but we see both these days, especially with the availability of pipes and smaller pipes that are mass manufactured. There is a tendency to also, you saw that example I showed there where sometimes, and we have seen sometimes penstock pipes as long as 2-3 kilometers because, the cost of civil works can be quite high, and especially in a remote area, it's actually cheaper to carry pipe than to carry cement and bring up sand, and all of these types of construction can be quite expensive. So where there are no roads, we actually see in places like Nepal a tendency nowadays to use more pipe and indeed use that option of just a pipe all the way.
There's another question regarding is mini microhydro suitable for remote communities? From your experience, if there is limited technical expertise, is it still something that is suitable for remote communities?
Yes, it's perfectly suitable for remote communities. In fact, I think for many remote communities, if they have these resources, since remote communities do often tend to be in the mountains, it is because of the ease with which people can be trained to operate it. Unlike an engine, there's no high temperatures and things to break down. Unlike solar, you don't have the issues of batteries and complicated management systems. So I do think that hydro does indeed have that advantage. Private sector probably will not be managing those systems. So I think the investment is then needed into the communities and also the operators. And again, as long as there's a sector somebody can call in case something breaks down, and the company that installed it can come over there, we do see hydro in a lot of remote communities.
Okay, and looking at the quality of local equipment, you said once the sector is developed, there's a private sector developing for turbine production, for even load control. What's your experience? Is this quality level sufficient?
Not automatically. So this is the key point, that in many countries that have even quite well established microhydro sectors, we see that the efficiency of turbines, the utilization factors tend to be low, and the cost of that is that the productive uses investment really doesn't happen. So if the power out of the turbines are not what they say, so that's one of the points I was making, the $500 per kilowatt types of installation. That might be what the nameplate says on the generator, but if you actually measure how much kilowatt hours gets produced, if you don't have good equipment, if you don't put in a controller that can make sure that it can take variable load without the operator having to sit there and open and close the turbine, the utilization remains relatively low. So it kind of defeats the purpose. So I do think that a lot of the sectors, I think, benefit from constantly upgrading the technologies. And that's important to build in any national programs that are out there, that indeed you are optimizing on the kilowatt hours and even better on the kilowatt hours used, rather than just the per kilowatt cost, which is low generally for markets where the equipment is not as good.
Mm-hmm. Okay, thank you. Since you stressed that much the productive use, I would like to remind the participants that there will be another webinar on productive use, in particular because we see there is a need for more information on that. That will be the third webinar in our series. There are a few more questions. And I would not allow to ask more questions since we are quite short in time, but if you want to type more questions, feel free to do so. We are going to take them up to inspire also our next webinars, so that maybe we are going to shift a little bit our topics depending on what are your requests or what's your feedback. So at the end, I would like to show you this overview table as I announced before. So I would ask Ranisha to switch to my screen. So what we saw so far was mainly related to different technologies, and now I would like to make a more comprehensive comparison between these different technologies. During the preparation of this webinar, we collected a number of information from different sources. So all this information came from many people who provided their input, but as you can see in the table, there are still a few cells which are simply empty because we didn't have reliable information. So if you have from your side any particular input or comment or criticism on this table, feel free to send it to us. So this table will be made available to the participants so that you can provide your input. I won't read through the whole table in detail because it's a quite long one, but I would like to stress a few things which I think are particularly important and which have already been discussed during the two presentations. So the first row that you see is the range of investment costs. We compare the most frequently used systems like micro mini hydro, solar battery and diesel, and the biomass gasifier, wind battery systems, and diesel systems. If you look at the investment costs, so for mini micro hydro, together with the biomass gasifier, the investment can be relatively low, whereas solar battery diesel systems, the cost per installed kilowatt is in general higher. Also for diesel, for sure, the initial investment is extremely low. But then if we come to the range of the levelized cost of energy in US cent per kilowatt hour, you see that micro mini hydro together with biomass is still quite cheap per kilowatt hour, whereas the diesel generator for sure is much more expensive because you have the continuous fuel price payment and you have to pay for the transport, which is often a difficult thing if you are in remote areas. If you look at the cost of energy for solar systems and for wind systems, they are quite higher compared to what you can achieve with micro mini hydro and biomass. Then these two cost components, or these two cost parameters, the investment cost together with the cost per kilowatt hour, is highly influenced by the local contribution, as Bikash also stressed several times. For mini micro hydro, the percentage of local contribution can be as high as 70%, in some cases probably even more. The same is valid for biomass gasifier. So this local contribution reduces the investment cost and also has an impact on the local availability of spare parts, which is much easier in the case of mini micro hydro, as well as for the biomass system. Maybe also a bit for the diesel generator. It's not so difficult to maintain it. There's some experience in most countries to do that. Wind systems really depends very much on the country where you are. So the local availability or the local contribution to a technology has an impact on how sustainably it can be maintained, if there is technical expertise in the country, if there are spare parts available. If we look at the resource assessment, someone already asked that, what to do if there's no flow data available. Actually, for any hydropower system and for any wind system, you really need measurements. So you have to measure the flow and you have to measure the wind speed. Whereas for solar systems, it's a little bit easier. To my knowledge, there's still a question mark, but to my knowledge, there's a database worldwide available where you can get insolation data. This is also the case for sure for hybrid systems, which include a diesel generator. And in that case, you just have to check, is diesel available and is transport, for example, during rainy season a problem? So resource assessment in these cases is more difficult for wind and for hydro, but the most difficult it is for biomass systems, because then you have to collect data on agro residues for at least 3 years, let's say. You have to check the supply chain, make a forecast. So it's quite a complex undertaking. Then to come to the cost drivers, as Bikash explained, the main cost driver is really the site conditions for the hydropower scheme. So depending on the steepness of the terrain, sorry, if you have any risk of landslide and so on, then this can be extremely expensive for the civil works. For PV and wind systems, the main cost component nowadays is really the battery part. And for biomass, it's always the question, what is the quality level of the equipment? For diesel, I already mentioned, the main cost driver is for sure the local price of diesel fuel and the transport of the diesel. Then if you look at the scalability and modularity of the system, for sure the PV systems have a clear advantage compared to others. A hydropower scheme or a wind scheme cannot be easily extended. For a biomass gasifier, normally you even start with several units because a biomass system needs daily maintenance. So if you have 2 or 3 units where you can switch from one to the other, you have the possibility to continue operation while you maintain a second unit. So since you have different units, it's also to a certain extent, at least it's scalable. But the easiest still is the PV, where except from the battery, it's easy just to add a few more PV panels if you see that the consumption is increasing. So as a general conclusion, I would say if you look at all the advantages, limitations, the first step might be to look, is there a very good hydropower site available? Because this is really a low-cost solution. If not, then the next step should be maybe to look at the biomass. Is there any biomass available? And is that technology in the specific country mature? Are there technicians who are capable to handle the technology? Is there equipment there? All these factors which can reduce the investment cost and the operation maintenance cost. And then if both resources are not available at all or not feasible for whatever reason, then PV, I mean, just from the cost point of view, PV and PV hybrid systems are also an option. For wind, there is one statement which I have put here in the table, that due to the high variability of the wind resource and the still high unreliability of wind turbines, and in addition the drop of the PV prices, wind becomes more a complementary source to save fuel or generate at night or during winter or rainy season when other resources are not available. So wind is somehow a bit filling the gap which cannot be filled by other resources. Then there's another row on the productive use. I mean, you can read all the details, as I said, and check if you have additional arguments. We thought it's essential to have this overview and to really check the different pros and cons of the technologies and to see how to make a best selection. Since I was explaining now about this table, I would hand over to Ranisha to check if there's any very burning question which we can raise before closing. Okay, we won't allow for any more questions because we are now already 5 minutes beyond our planned schedule. So I would like to thank you very much for listening, and I would hand over to Ranisha for the closing. I think in general you got a very good overview on the different technologies. I mean, we didn't have sufficient time to go into the technical details, but I hope you got some more information which could help you to make a good decision in the future for decision on which renewable energy is the most appropriate in a specific case. But in general, if there is more demand, we would also tend to have another webinar on that topic. So let me hand over to Ranisha, and thank you very much for listening, and thanks in particular to the presenters.
Thank you, Heidi. And now some final announcements. As you all asked about the webinar material, and Heidi already said, all these materials will be uploaded to Energypedia, and we will share the link shortly. In case you cannot find the link or have any problem, please send us an email at info@energypedia.info. Also, please stay tuned for our upcoming webinar on grid interconnection on 1st of June and productive end use in early July. We will also share the link shortly. Once you close your webinar, browser, a pop-up window with the feedback survey will appear. Please give us your valuable time by filling out the survey. This survey will help us to improve the quality of our presentations. Heidi, could you go to the next slide, please?
Just a second.
Sorry, we had some technical issue, but the last slide was about thanking to all our organizers and supporters who have helped to make this webinar a success. And a special thank you to Dipti, from the coordinator of ASP.NET, and Heidi for working on the concept and helping us put together the webinar. And thank you to all other people who gave us feedback and everything. And thank you for today, and we look forward to seeing you again in our next webinar. Till then, take care. Bye-bye.